So let's continue with the book back question. The fourth question. So there's Jupiter, okay? One of the satellites of Jupiter has an orbital time period. The satellite of Jupiter has a time period 1.769 days, and the radius of the orbital of the satellite of the Jupiter is 4.22 into 10 to the power 8 meters. Show that the mass of the Jupiter by the mass of the Sun is 1 by 1000. The time period has been given and you want relation with mass, then immediately go for this formula where you remember we did a T square R plus H the whole cube is equal to T square G R square by 4 pi square, and instead of G R square you can replace it as capital G into M by 4 pi square, and this can be called as R cube, R plus H, because R is the radius and H is the height, and so from the surface, so R cube. And so thus you have a relationship. What is T square therefore? Is 4 pi squared R cube by Gm. That's T square, and let's therefore write the time period of so let's write the formula for time period of this satellite of Jupiter, which is 4 pi square orbital radius of the satellite of the Jupiter the whole cube by the capital G, which is always a constant, the mass of the Jupiter. The capital M stands for the mass of the bigger object, which is only the Jupiter. And then compared with Earth and the Sun, okay, which is 4 pi square radius of the Earth's orbital around the Sun the whole cube by the gravitation and mass of the Sun. They want the ratio of this time period. No, they want the ratio of them, not the time period. They want the ratio of the masses. So then ideally you should have written mass of the Jupiter from here. Mass of the Jupiter is capital M, which is 4 pi square R cube by T square into G, divided by mass of the Sun. This mass of the Jupiter, top, mass of the Sun at the bottom, which is 4 pi square. This is orbital radius of the satellite of Jupiter. This is time period of the satellite around the Jupiter by 4 pi square radius of the Earth around the Sun, the cube, by time period of the Earth around the Sun square by G. The capital G get cancelled, 4 pi square get cancelled. Thus you know mass of the Jupiter by mass of the Sun can also be radius of orbital of the planet around the Jupiter, which is 4.22 into 10 to the power 8 the whole cube, by the time period of the Jupiter's planet, which is 1.769 days. That's the time period, and this goes up into time period of the Earth is 365 days. Let's keep it as days because this is also days and this is also days. Let's leave it like that. Divided by R cube, RE, Earth's orbital on the Sun is 1 astronomical unit, which is 1.496 into 10 to the power 11 the whole cube. So just do this calculation, make sure you are getting an answer which is 1 by 1000, approximated to 1 by 1000, and that's all. So these are the values you're supposed to substitute. Keep days at days so it's easier to calculate. And that's about it. Okay, so next question is again, this is for this one where it's T square is proportional to R cube. Yeah, that I'm not directly using that because I need to find a formula for capital M, so I have to necessarily do this and take it as a satellite and the time period of the satellite, and that's where you get a capital M and you have to cross multiply. So we can't just use the final conclusions of the Kepler's law there. Okay, so let's go to next question. The next question is the fifth question, the textbook book back. The galaxy consists of 2.5 into 10 to the power 11 S stars, each of 1 solar mass. Oh, 2.5 into 10 to the power 11 this S stands for solar mass, okay, and the conversion is 1 solar mass is 2.5 2 into 10 to the power 2 into 10 to the power 30 kg. 1 solar mass is 2 into 10 to the power 30 kg. So 2.5 into 10 to the power 11 solar mass is 2.5 into 10 to the power 11 into 2 into 10 to the power 30. So this will be 5 into 10 to the power 41 kg. So thus you get the mass of the galaxy. Let's assume that a galaxy consists of so many stars, each of 1 solar mass. Oh, 1 solar mass itself is 5 into 10 to the power 1 solar mass is 2 into 10 to the power 30, but there are so many 2.5 into 10 to the power 11, so you multiply that, you get the total mass of all the stars in the galaxy. How long will a star at a distance of 50,000 light year from the galactic center take to complete one revolution? So again, it's talking about time period. We just saw a formula here, the T square formula. T square is equal to 4 pi square R cube by capital G into capital M. And so 4 into 3.14, the whole square is 9.87 if you can memorize it. And the radius is okay, the radius has not been given, but you have to calculate the orbital radius. This has been given as 50,000 light year. 50,000 light year is 50,000 into light year. 1 light year is 9.46 into 10 to the power 15 meters. So just multiply this. It is 4.73 into 10 to the power 20. That is the answer that you get for this. And so take it and substitute it here. So it's 4.73 into 10 to the power 20, the whole cube, divided by capital G, which is 6.67 into 10 to the power 11, into capital M, which you just calculate the galaxy's mass, 5 into 10 to the power 41. So this you have found T square, and then do a square root of it, you'll get T. It turns out to be 3.54 into 10 to the power 8 years, but actually you get the answer in seconds, and then they are converting into years by dividing by 60 for a minute, and 60 for an hour, and then by 24 for days, and the 365 for a year. And so then dividing, you get it in years, but you can leave it like this. You don't have to really find the final answer, or you can find whatever the answers in seconds is also fine, and you have to find the square root of this. So you must remember the relation between this T square. No, let's start remembering this itself. Instead of writing an R plus H the whole cube is equal to T square G R square by 4 pi square, and replacing this as capital G into capital M, and replacing this as R cube, and then writing a formula for an M or a T. Let's now try to memorize this formula itself, where you should, T square is proportional to R cube. So the constants of proportionality in it is nothing but a 4 pi square by capital G into capital M. If you can memorize this, then we don't have to go back and forth and deriving anything. Just use this formula where you have time period, and the question is about time period of the galaxy, and the radius of the orbital has been given. And so it makes it very, very easy for us to do this calculation. So let's go to sixth question. Sixth question in the textbook: if the zero of the potential is at infinity, then all of these are negative potentials. The total energy of an orbiting satellite is negative of its kinetic and potential energy. Okay, so then to approve, choose the correct alternative. The total energy of an orbiting satellite is negative of total. Total energy is always negative of kinetic energy, not potential energy. So that is already known. I'll just teach you the derivation. The total energy is kinetic energy plus potential energy. A potential energy is minus k is d square by r, and the kinetic energy is k z e square by 2r. And you know how we got this kinetic energy? Half mv square is the kinetic energy. Okay, and in this you're equating this kinetic energy. You want k z e square by 2r. How did you get this k z e square by 2r? Once again, I'm getting it. Sorry, in this lesson I just went to electrostatics by mistake. Potential energy is minus g capital M small m by r, and kinetic energy will be g capital M small m by 2r, and so on. So that's your kinetic energy, and therefore the total energy is minus g capital M small m by 2r. That's the total energy is negative of kinetic energy. So that's the derivation you need, negative of kinetic energy, and so that completes this. And supposing you want to get this formula, let's equate mv square by r. mv square by r is equal to g capital M small m by r square, where r and r get cancelled. You multiply both sides with a half, thus you get kinetic energy's formula to be g capital M small m by 2r. So this is the proof for writing total energy is negative of kinetic energy. And so that's about this. In case they ask you for a proof. So let's go to next question. The B subdivision. The energy required to rocket an orbiting satellite and out of the Earth's gravitation. So a satellite is orbiting around the Earth. Okay, that's with an orbital velocity. You want it to escape into the Earth. Okay, the energy required to rocket an orbiting satellite out of the Earth's gravitational influence is more or less than the energy required to project a satellite at the same height out of the Earth's influence. Okay, supposing you are projecting a satellite to the same height, and the second case is you are projecting the satellite to the same height but allowing it to orbit. Two different cases, and they are saying the energy required for orbiting, putting it in orbit, will be less than raising it to that particular height and make it stand there. The energy required to rocket an orbiting satellite out of the Earth's gravitational influence is more or less, we have to choose, than the energy required to project a stationary orbit at the same height. The energy required to rocket an orbiting satellite out of the Earth's gravitational influence is always less than that of the. So can we say escape velocity? Escape velocity is actually root 2 times orbital velocity. Escape velocity we know is root 2 times orbital velocity. But that's not what they are asking here. So let's understand this. An orbiting satellite has to be taken out of the Earth's gravitational field. So then the change in the energy for that is actually half m ve square minus half m v naught square. That is orbiting kinetic energy, and this is escaping kinetic energy. And so let's subtract these two. So half into m into escape velocity formula v is root of 2 gm by r. So it's 2 g capital M by r. Okay, where and this is half into m into orbital velocity is gm by whole square. So gm by r. So in this the 2 and 2 get cancelled, or so then therefore you get g capital M small m by r minus g capital M small m by 2r. So the answer will be g capital M small m by 2r. So that's the answer for delta E1 that you get. For this, to achieve this from orbital, you're going to escape it. And the next one is just to take it for the stationary object. You're just taking it to a height h. The same height h, you're just taking it. You're not. So you just take it to a height h, and it's just delta E2 is half m ve square. Okay, this is from orbital to escape. This is directly just to escape from the ground. So it's half into m into 2g capital M by r, which is 2 and 2 get cancelled. G capital M small m by r. The fact that this is your second equation shows that this is divided by 2. So delta E1 is definitely lesser than delta E2. The energy required to put something in an orbit is definitely, that is putting in an orbit. Energy required to take something in an orbit to escape is lesser as can compared to just taking a stationary object to a height h. So this is the explanation you got to write in here. So let's go to next question. Next question is the 7th question in the textbook. Does the escape speed of the body from the earth depend on the mass? No. It does not depend on the mass. Escape speed is root of G capital M by R, and so then therefore you know that it's definitely not going to be dependent on small m. Is independent of small m. Escape velocity, right? Root of 2gm by R. Sorry. So it's independent of small m. And the second part of the question is the location from where it is projected. The location from where it is projected, the energy required to rocket and orbit satellite. No. Does the escape speed depend on the location? Yeah, it depends on the latitude, right? It does depends on the latitude, and so the escape velocity depends on the latitude of the location from. Yes, just say latitude. It depends on latitude. You know, latitude is omitted, but I've taught you in class. So the next is the direction of projection. It does not depend on direction of projection. Whether you launch the satellite right up or like this, it still is going to escape in the outer atmosphere. It doesn't matter. And so then the escape velocity is independent of the direction. And then the last is the height of the location where the body is launched. As the gravitational potential depends on the height of the location, so escape velocity also depends on the height of the. Supposing it's not getting launched from the surface, it's getting launched from a height h. So obviously, when you integrate, you're going to put the r to infinity. Instead of that, you're going to put some distance h plus r from the surface to infinity. So it does vary. The gravitational potential also, energy also varies. Hence, the velocity also, escape velocity will also vary. So that completes the option number 7. So latitude depends. That's next is about independent of projection, independent of direction of projection, independent of direction, and then dependent on height from which it's getting projected. Okay, so let's go to next question. Is the 8th question. A comet orbits the sun in highly elliptical orbit. Does the comet have a constant linear speed? No. Angular speed? No. Because angular velocity, linear velocity is r times angular velocity. The linear velocity varies, angular velocity is also varying. Angular speed. Angular momentum. Angular momentum will remain conserved. Angular momentum, that's the only thing which remains conserved. Okay. So angular momentum conserved. Next, kinetic energy. Kinetic energy, since the linear velocity keeps on changing, angular velocity keeps on changing, kinetic energy also keeps on changing. Next is about potential energy. As the distance of the planet from the sun continuously changes, the potential energy keeps on changing. Obviously, when the kinetic energy is changing, the potential energy will also change accordingly. You know, when the kinetic energy is more, potential energy will become less. The total energy always remains conserved. Okay, so that's the answer for all this. So let's go to 9th question. for a person who's in the astronaut in space, the feet will never be affected, only the upper body will get affected. Swollen face, headache, orientational problem will all occur because blood flow is not there. Due to no gravity, the blood will not flow down, it will all get accumulated in the upper body, and that results in a swollen face, headache, and orientational problem. So let's go to 10th question. 10th question is the gravitational intensity. Okay, they've given a hemispherical shell, and they have indicated some arrows which represents the electric field, which represents the electric field's direction. Is it so? This is A, this is B, and this is C. The gravitational intensity at C of the drumhead defined by a hemispherical shell has a direction indicated by the arrow. So complete the hemisphere to a sphere. Complete it to a sphere. Imagine it to be a sphere. Okay, so in that case, the gravitational potential V is a constant. E is equal to minus dV by dr, and since you know that E is 0, the net electric field will be 0 due to sphere. Can you see, everything will get cancelled, the vectors will get cancelled out, and so at the center the electric field can be 0 because of the vector cancellations. And so when electric field is 0, we can say the potential turns out to be a constant, because a differentiation of constant only can be 0, therefore which makes the potential to be a constant. So can I say hence in the hemisphere the net is 0 at C. The electric field cancels out and becomes 0 at C. For a hemisphere, the net gravitational intensity will be downward direction. So can you imagine it, if it is like a sphere, all of them will get cancelled, all the vectors will get cancelled. But unfortunately, it's only a hemisphere, which means you can imagine that the vectors are going to be like this, and it's not getting cancelled, it will be in upward direction, but the gravity will always pull it down. So then therefore you say C is the net resultant. Okay, so that's that question. And let's go to next term for the 11th question. Is the same diagram. They seem to be having some other arrows such as G and a D and a E and a F, and again here again the same explanation, and so then E will be the answer. So let's go to next question. Similar reasons inside. This is a common reason for it. The electric field for a symmetrical it's not electric field, it's gravitational field intensity is what is represented like this, and this is a vector. For a sphere, gets cancelled and becomes zeros at the center of a sphere, therefore potential is a constant. So not only at the center, you can take it at any point for any symmetrical position, all these will get cancelled. So inside of it always E is 0 and hence V is a constant, and that concludes that if you take the upper half, it will act downward, the resultant will all act downward, and so E. So let's go to 12th question. A rocket is fired from Earth towards the Sun. At what point on its path is the gravitational force on the rocket 0? So a rocket is fired from the surface of the Earth to the Sun. So at some point in between, you don't know where exactly. You can keep one as this distance is r. From the center, it's going to be r. You can call one distance as x, another distance is r minus x. And the rocket is fired from the Earth to the Sun, which means only from the surface of the Earth, right? From the Earth to the Sun, a rocket is getting fired, and in somewhere here you don't know. Then suppose the distance between them is r. Okay, let's see. The mass of the Sun is 2 into 10 to the power 30 kg. Mass of the Earth is 6 into 10 to the power 24 kg. The orbital radius of the Earth around the Sun is given to be 1.5 into 10 to the power 11 meters. So you assume that somewhere between, okay, let's consider this as x and this as r minus x. Let's not take from the centers in this sum, because the launching of satellite happens only from the surface of the Earth. So this is x and that is still the surface of the, it's not going to penetrate into the Sun. So you don't have to take the radius of the Sun into account. This is capital M, this is Sun's mass, and this is Earth's mass. Okay, so this is x and this is r minus x, and at this point somewhere between them the gravitational force is 0. What is the formula for this? Just G. Gravitational force is G into mass of the Earth. Okay, let's consider a small rocket mass is m. G into mass of the Earth into small m by x square is equal to G into mass of the Sun into small m by r minus x the whole square. This force and this force is going to get cancelled for the net force to be equal to 0, or the net gravitational force to be 0 on the rocket. M and M get cancelled, G and G get cancelled. Therefore it's mass of the Earth by mass of the Sun is equal to x square by r minus x the whole square. And mass of the Earth has been given to be 6 into 10 to the power 24. Mass of the Sun is 2 into 10 to the power 30, which is equal to x square by r is given as 1.5 into 10 to the power 11 minus x the whole square. Now you can just cancel everything and solve it and get the value of x. Okay, in fact this will become 3. This will become 3 into 10 to the power minus 6 is equal to x by 1.5 into 10 to the power 11 minus x the x. So therefore you are going to find a square root of this, and as you can say a square root of root 3 is 1.732 into 10 to the power minus 3 is equal to x by 1.5 into 10 to the power 11 minus x. So on cross multiplying you get to multiply this and then consolidate x. Pretty lengthy calculation, but let me try. Okay, let me approximate this to 1.7. 1.7 into 1.5 is 7 5s are 35, 5 1s are 5, 8, 7 1s are 7, 1 1s are 1, 5 into 55. So it's 2.55 into 10 to the power minus 3 minus 1.732x is equal to x. So take it that side. It's 1 plus 1.732, it's 2.732x is equal to 2.55 into 10 to the power 3. So x is equal to 2.55 into 10 to the power 3 by 2.732. So can we say it's what is x? The answer that they have got for x is 2.59 into 10 to the power 8. Just have to see if you will get anywhere near this. No, I don't think so. So what is the mistake? Mass of the Earth 6 into 10 to the power 24. We calculated this mass, capital G, M in mass of the Earth by mass of the Sun. Correct. So then directly they taken root, but it's okay. So you have 2 into 10 to the power 30 and 6 into 10 to the power 24. So this goes up 3 into 10 to the power minus 6, and the square root of it is x by 1.5 into 10 to the power 11 minus 6. So root 3 is 1.7. Multiplying these two, 2.732x. What would this become? 2550 by 2.732. Still not getting anywhere closer to this answer. Yeah, 1.732 10 to the power minus 3. I forgot that. Shit. So then make sure that you're correcting it. I'm sorry. So then take all the x together. You get x into 1 plus 1.732 into 10 to the power 3. 10 to the power minus 3 is it? Is 2.55 into 10 to the power minus 3. So in order to get a 10 to the power minus 3 here, you can, to simplify this faster, you can do x into multiply and divide by 10 to the power minus 3. So 10 to the power minus 3 can throughout get cancelled. This will be 2.53 is equal to, this is 1000 x into 1000 plus 1.732. So x into, can I say 1001.732 is 2.53. So x will be 2.53 by 1001.732. Let's approximate it to 2.53 by 1002. Okay, and then let's find the answer for this. So let's assume this is closer to 1. So can I write, if I assume, approximate this to 1, which means into 10 to the power 3 will be there. This can go up as 10 to the power minus 3. And it will be 2.53 into 10 to the power minus 3 still. Calculation is a problem. Some mistake somewhere. Okay, this multiplication is also incorrect. The calculations are wrong. Please use a calculator if you want. Okay, this and this multiplication, I didn't take the powers into account again. Can you see? When you multiply it should become 10 to the power 8 with a positive value of 10 to the power 8 here. So the whole thing changes. And so then from here you try to calculate and see if you're getting the right answer. I'm sorry I've made some mistakes in calculation, but otherwise you should get this answer. Conceptually this is what you should do. So make sure you're correcting your mistake and consolidating your x. Okay, so that's about this sum. And let's go to next question. Next question is the 13th question. How would you weigh the sun? So they want the mass of the sun, and I know that there is a time period formula which relates to mass. We just seen it. Okay, and we also decided that we're going to memorize this formula, which is this t square is 4 pi square by gm into r cube. So using this formula, if you see they want the mass of the sun, then they have also given the orbital radius. Then rest of it is all constants. How would you weigh the mass of the sun? Oh, they want the mass of the sun, and you know the Earth's orbital and you know the time period. Therefore, you can cross multiply, get the mass of the sun. So I'm not going to do that sum. It's very, very simple. As long as you remember that formula, then it's fine. So let's go to the next question, which is the 14th question. The 14th question: a Saturn year is 29.5 times the Earth year, which means a Saturn is going to take 29.5 times the time taken by the Earth, time of the Saturn. Okay, so then the mean orbital radius of the Earth, how far is the Saturn from the Sun? If the Earth's orbital radius RE is 1.50 in 10 to the power 8 kilometers, what will be the radius of the Saturn? Okay, and you know that time period of the Saturn, t square is proportional to r cube by time period of the Earth the whole square is equal to radius of the Sun the whole cube by radius of the Earth the whole cube. Not the radius exactly, the radius of orbital. Radius of orbital of the Sun and radius of orbital of the Earth. So it's 29.5 times TE. TS. So whole square into TE square by TE square, where TE square get cancelled, of orbital of the radius of orbital of the Saturn around the Sun. Saturn around the Sun is unknown. Saturn around the Sun, but we know the radius of the Earth around the Sun, which is 1 astronomical unit, which is 1.496 into 10 to the power 11 whole to the power 3. (1.496 into 10 to the power 11). They're writing it in kilometers. Why? Because they have given it. You don't have to write this one astronomical unit here, because they themselves have specified it to be 1.50 into 10 to the power 8. So to convert into meters, you can, or you can keep it in kilometer only and then do the sum. So just cross multiply and get the orbital radius of the Saturn. So let's go to 15th question. Body weighs 63 newtons on the surface of the Earth. 63 Newton on the surface of the Earth. What is the gravitational field on it due to the Earth at a height equal to half the radius? What is the gravitational force on it due to Earth at a height equal to H is equal to R by 2? So gravity at a particular height formula. Okay, there are two formulas. Gravity at a particular height is also R by R plus R square by R plus H the whole square if the height is big, and here obviously it's big here. So R square by R plus R by 2t whole square. It's R square by 3R by 2t whole square. So it's 4 by 9. So that is into gravity on the surface. Obviously gravity on the surface. Gravity on the surface, you know, is 9.8, or you can write it as G. And what are they asking? They are not asking, they are saying body weighs 63 newtons on the surface of the Earth. 63 newtons means that it includes gravity. And so then therefore, this 4 by 9, it includes gravity, it's 4 by 9. And so then since it includes gravity, you just have to write 4 by 9 of 63, which will directly give you your newtons. Okay, so then that's about this question. So 16th question. Assuming the Earth to be a sphere of uniform mass density, how would the body weigh halfway down the center of the Earth? So depth is equal to R by 2. Depth will be, okay, gravity at a particular depth is G into 1 minus D by R, or G into R minus D by R, where G into R minus R by 2 by R, which is G into this, an R by 2 divided by R and R get cancelled, G by 2. So if it's, a body is going to weigh 250 newtons, since the gravity is getting halved, it's going to weigh only 125 Newton on that particular depth. Okay, so that answers this question. 17th question. A rocket is fired vertically with a speed of 5 km per second from the Earth's surface. How far from the Earth does the rocket go before returning to the Earth? How far from the Earth does the rocket go? So they are asking for that height. They are asking for the height through which rocket can go before it returns back to the Earth. So which means it's going to come back to the Earth. Rocket is fired with a vertical velocity 5 km per second. You know, escape velocity means it has to be 11 km per second. Obviously it's not going to escape, it's going to come back. That is very clear. So you have to find how much height will it go for this velocity 5 km, how much high will it go. What you have to do is you should take the kinetic energy plus potential energy on the surface will be equal to kinetic energy plus potential energy at a particular height. Okay, what is kinetic energy on the surface is half m, this velocity square, v square, plus potential energy on the surface is minus g capital M small m by capital R is equal to the kinetic energy plus potential energy at the top. On the top point, there's no kinetic energy, there's only potential energy, because at the topmost it's going to come down, which shows the velocity on the top is going to be 0. So kinetic energy is 0. It has got only potential energy, which is minus g capital M small m by R plus h. So just write this and cancel the small m throughout. So you get v square by 2 minus gm by capital R is equal to minus gm by R plus h. So you get it like this. Now you can write what is this, write v square, just multiply throughout with the 2 gm by R is equal to minus 2 gm by R plus h. And you're going to find what is R plus h, right? So if you take an LCM here, you get v square R minus 2 gm by R is equal to minus 2 gm by R plus h. Let's reciprocal this. And R plus h by 2 gm is equal to taking the negative sign to the other side and switching the values. Okay, you have to reciprocal it, right? So this has to come in the denominator. Switched 2 gm minus v square R in the denominator and an R on the numerator. Therefore, R plus h is equal to R into 2 gm by 2 gm minus v square R. And therefore, to find h, you can take the R to the other side. And you can take R also common. And you can get a 2 gm by 2 gm minus v square R minus 1. Substitute the respective values and just get this answer, that's all. Okay, so that's at least till here you should be able to write. And for you to understand that how high will it go before it comes back, you should do conservation of energy. This is the only way in which you can do the sum. So let's go to 18th question. The escape velocity of the projectile on the Earth's surface is 11.2. We know this already, 11.2 km per second. The body is projected out with thrice this speed. Okay, what is the speed of the body far away from the Earth? 3 times the speed. So the projected velocity is 3 times the escape velocity. This is the initial velocity with which it's getting projected. You should know that this escape velocity, so you know that the velocity with which it's getting projected, the velocity with which an object is getting projected will be sufficient enough to provide it with an orbital velocity and also allow it to escape and go into the outer atmosphere with an escape velocity. So half get cancelled, m get cancelled. The velocity with which you are getting project should be v0 square plus ve square. You already know that this can be written as 9 ve square is equal to v0 square plus ve square. Taking that side, 8 ve square is equal to v0 square. And we know what is ve from here. So then v0 therefore is 2 root 2 into ve, and 2 root 2 into 11.2 km per second. So you'll get the orbital velocity. So what is the speed with this speed of the body far away from the Earth? Let v0 be the velocity of the projectile after escaping gravitational pull. So just remember this, the velocity with which I am propelling should be enough for it to go to a particular height and also allow it to escape. And so if they want me to find the velocity at a particular height, I would take this as a velocity at a particular height and do it. Okay, so let's go to, that's very difficult in my opinion. So next question is, a satellite orbits the earth at a height of 4,400 kilometers above the surface. How much energy must be expended to rocket the satellite out of the earth's gravitational influence? How much energy should be expended? So the mass of the satellite is 200 kg. Mass of the satellite is 200 kg. Satellite can be written small m. Mass of the earth is given, radius of the earth is given. Okay. How much energy can be expended to the rocket satellite out of the gravitational influence? The total energy is required is always negative of kinetic energy. We know this formula. And the kinetic energy's formula is minus G capital M small m by 2R. And this is the energy required. That's all. G capital M small m. What is G? Minus G is 6.6 into 10 to the power minus 11 into capital M is the mass of the earth, which is 6 into 10 to the power 24, into small m, which is the mass of the satellite, which is 200. Okay, everything is in kg, divided by 2 into R, 2 into R, which is R actually R plus H, right? Where this R can be written as an R plus H. And capital R is 6.4 into 10 to the power 6, plus height is 400 into 10 to the power 3. So all these values will give you this. It's very simple. I don't know, Aurora has elaborated more on it. You just can write this and leave it like that. Let's go to the next question. In the order that I did in the class, I went for the 21st question. The two heavy spheres of mass 100 kg and radius 0.1 meter are placed 1 meter on the table. So mass, this is also 100 kg, this is also 100 kg. Of radius 0.1 meter. This radius is also 0.1 meter. It's placed 1 meter apart. What is the gravitational field and the potential at the midpoint of the line joining? And the gravitational field will be 0. Because it's the same mass and same distance, can I say the gravitational field at the midpoint will be 0? Let me check. Two heavy spheres which mass 100 kg, radius 0.1 meter are placed 1 meter apart. What is the gravitational field? Okay, so definitely the gravitational field, with regard to gravitational field, it will be 0 only. Because if it will be in this direction, that field direction will be in this direction, pulling it towards each other. So they both cancel out. The same mass. Okay, so then you obviously the gravitational field is E, which is F by M. So small m get cancelled. G capital M by R square of this, and the G capital M by R square will get cancelled because one is in negative direction, other is in positive direction. So they both get cancelled. Same values. So the net field becomes 0. Net gravitational field becomes 0. Then they're asking for potential at the midpoint. Potential formula is minus, for this is minus G capital M by small r, and for this minus G capital M by small r, and both the potential will have to be added because potential is a scalar, whereas gravitational field is a vector. In vectors, if you see opposite direction, you need to subtract, but this is a scalar. You just simply add minus Gm by r minus Gm by r, which will be minus 2Gm by r. And so if you know the respective values, just substitute and get the answer. That's about that question. Then the 20th question, which I didn't do in the class, I'll do it now. The next question is the 20th sum. Two stars of one solar mass. You know, one solar mass is 2 into, you have to multiply it for the conversion of solar mass. You just have to multiply it with 2 into 10 to the power 30 kg, which is just the mass of the sun. Just multiply it with 2 into 10 to the power 30 kg. So 2 stars, each of one solar mass. So 2 into 10 to the power 30 is the mass, and they are approaching each other for a head-on collision. When they're at a distance of 10 to the power 9 kilometers, which is 10 to the power 12 meters, the velocity becomes negligible, which means at that point there is no kinetic energy. So the potential energy alone exists, and the potential energy will be minus G capital M into capital M, which is 2 solar masses, by the distance which is 10 to the power 12. That's the potential energy, which is minus G M square by 10 to the power 12. That's the initial potential energy. And when these two masses are colliding, the distance between them is radius plus radius, which is 2r. And the radius of each star has been given. So 2 into 10 to the power 4 kilometer, which is 2 into 10 to the power, say 7 meters, will be the distance in the second case, when the final potential is G M square by the distance is 2 into 10 to the power 7. And U final minus U initial will be, or U initial minus U final will give you delta U, the change in the energy, which you can calculate, and that value they have written it to be Gm square by 2 into 10 to the power 7. Okay, so then so they've got this as the value, and that's the change the energy. What is the question? What is the speed which you got? Now that you got the change in the energy, the change in the potential energy will also be equal to the change in the kinetic energy, delta Ke, which is final kinetic energy minus initial kinetic energy. Okay, the initial kinetic energy is 0, because at that instant when it's 10 to the power 9, we consider the velocities to be 0. So final kinetic energy of one is half mv square for both of them together. So it's a half mv square plus half mv square, and they are scalar quantities, so just add, so it will become mv square minus 0. Therefore that will be the final kinetic energies of both the stars, and that can be equated to G into m square by 2 into 10 to the power 7, where m and m get cancelled, and you just find the square root of this, you get the actual answer. And that also again is a very difficult sum for me, but as long as you've understood this and you're able to write in the exams, that's fine.